This is Physics 2212 Lab 4 going over circuits and capacitors. Now in this lab we will be understanding the behavior of circuits, resistors, and capacitors, and we will be using a virtual tool to facilitate this. And a preview of the results, we get that the experimental model data is similar to the data reached through equations. Now principles to get out of the way, we first have Ohm's law, so voltage equals current times resistance. Capacitance, capacitance equals charge divided by voltage, and then the potential difference of a capacitor plus the potential difference of a resistor is equal to 0. Now observations with the circuit on the right, we have two 1.5 volt batteries, a 47 and 100 ohm resistor, and then 2 ammeters, and then the predicted we can get current with I equals V minus, or divided by R, where I is current, V is voltage, and R is resistance. We can get our current equal to 3 volts, so the two 1.5 volt batteries added together divided by 147 ohms, the 47 and 100 ohm resistor, equals 0.02 amps for our current, and we can see that the actual current as seen right here and the ammeter is equal to 0.02 amps. And here we take out the bottom ammeter and replace it with the voltmeter, and then we can see our predicted is going to be the sum of the two batteries voltages, so 3 volts, and then the actual we see is 3 volts, and this is an open circuit, so there is no current. Now once we close up the current with a wire, or close up the circuit with a wire, we can actually find the potential differences at different points using this map below on this circuit above. At the different points, using the voltmeter, we can find the potential difference at B minus A here to be equal to 3 volts at the batteries. D minus C, so at the 47 ohm resistor, equal to negative 0.96 volts. And then at the 100 ohm, F minus E equals negative 2.04 volts. And then we can use the potential difference of the round trip is equal to the sum of the potential differences we found is equal to 0 volts. So we get 3 minus 0.96 volts minus 2.04 volts, and that follows the loop rule given that it's equal to 0, so the round trip potential is equal to 0. Now here in this circuit on the right we have an ammeter parallel to a 100 ohm resistor, and we have the current actually increases from 0.02 amps to 0.06 amps, and this is because there is less current contacting resistor, so less resistance. As your resistance decreases, your current increases as seen by IR equals V. Now you could actually calculate the resistance using voltage divided by current, so the 0.96 volts for the 47 ohm resistor, here D minus C, 0.96 volts, 0.96 volts divided by 0.02 amps is going to be equal to approximately 47 ohms, and this is approximately because of precision with the ammeter, and then we could do the same for the 100 ohm resistor as well. Now here we have some circuits with 10 ohm bulbs, a 20 ohm bulb, a 9 volt battery, and then a 200 millifarad capacitor. And with the battery and the 10 ohm bulb, we can see that it starts on bright and then it dulls to nothing and ending at 0 current. And then with no battery, we get the same effect. And we repeat that for the 20 ohm bulb, and then we can actually use a stopwatch to time the charge and discharge rates. So with the 10 ohm, it charges for about 10 seconds and then takes 12 to discharge. And then for the 20 ohm, it takes about 17-ish to charge and then 22 to discharge. Now we can use the equations above to calculate the change in potential difference of a capacitor, and we can actually take the line of best fit from graphing all the data points. So we get y equals 0.16x, and then obviously plus our error value of 0.15. Now using the slope from before the 0.16, in a situation with a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm bulb, we can use that slope from before to get RC equal to 6 seconds, and this is equal to the expected, where resistance times capacitance, so 30 ohms for resistance for the bulb times 0.2 for capacitance equals 6 seconds. Now what if we were doing the lab in real life and used an actual ammeter instead of an ideal one? What would be different about the real one, and how would it affect the circuits hooked up to? Now, how it would work in actuality is that it would just have some resistance, meaning that current would be lower due to V equals IR. Now, what if we were doing it in real life and used a real battery to charge up a real capacitor with no resistor in the circuit? How quickly would the ideal model predict the capacitor to reach full charge, and then would this happen in real life? If you had no resistor in the model, it would actually immediately reach full charge. But while in actuality, wires do have some resistance, so this would not actually occur in real life. Thank you.